So finishing out Chapter 7, Section 7.5, I wanted to show you just a few other kind of trig equations. Now we want to break these down into the sort of techniques we used in the last section. So if I start with something like 1 plus sine theta equals 2 cosine squared theta, what I would prefer to do is turn this into something that only involves one of these two trig functions, either the sine or the cosine. That's what's going to allow me to use the techniques from the last chapter, where I either applied inverse trig functions or could solve for it precisely using the values in the table. So to do that, I'm going to need to use some identities. I'm going to either need to write sine in terms of cosine or cosine squared in terms of sine. This one I think is a little bit easier to deal with because we've got our Pythagorean identity. So 1 plus sine theta equals 2 times, by the Pythagorean identity, 1 minus sine squared theta. That goes in place of cosine. Multiplying that all out, I've got 1 plus sine theta equals 2 minus 2 sine squared theta. If I get all these on the same side, here's what I'm left with. 2 sine squared theta plus sine theta minus 1 is equal to 0. Now, this looks a little strange, but think of it in this term. If it was instead 2x squared plus x minus 1 equals 0, this is a quadratic. If you treat the sine of theta as your variable, this is just the same thing as this quadratic, and this factors. 2x minus 1 times x plus 1. So this factors into 2 sine of theta minus 1 sine of theta plus 1 is equal to 0. And now, all I need to know is that one of these two pieces is equal to 0. So, if 2 sine theta minus 1 is equal to 0, sine of theta is equal to a half. On the other side, sine of theta plus 1 equals 0. Sine of theta equals negative 1. Well, those aren't actually too difficult to deal with. In the first case, this is going to happen when theta is equal to either pi over 6 or 5 pi over 6. And in the second case, when theta is equal to 3 pi over 2. And as usual, plus 2k pi to both of them based on the period of the sine function. So we broke it down to this point here, these guys, which we were able to solve with our techniques from the last section. But to do that, there were a couple things that needed to happen first. This cosine, I needed to turn it into a sine. You could have also found a way to turn the sine into a cosine, and you need to experiment with this. There's not always a guaranteed right way to deal with these. You can try different approaches. There's more than one path to a correct solution here. But you'll usually find that the algebra gets worse in one case over the other. In this case, by turning this into a sine, the algebra in through here was not so bad. And then once we got it to here, it's based on our earlier techniques, and we added our 2k pi to respect the period of the sine function. So that's what you want to deal with, applying the trig identities when you've got multiple trig functions inside of an equation. The other case we haven't really looked at yet is things like 2 sine of 3 theta minus 1 equals 0, where you don't just have a theta here, or an x, or whatever variable you have. You've got a multiple of that variable. Now I'm going to solve this the same way I did on the last slide to get sine of 3 theta equals positive 1/2. Well, we solved previously, here in blue, sine of theta equals 1/2, and we found out that theta was equal to pi over 6 or 5 pi over 6. So what that tells me here is that 3 theta is equal to pi over 6, or 5 pi over 6. Well, I should be able to divide those both by 3 to get theta pi over 18 plus 2k pi, or 5 pi over 18 plus 2k pi. So what I did, once I got to here, I treated this 3 theta like its own variable. I knew what that had to be equal to, and once the trig function's gone, once you've got something involving just this theta, maybe it's multiplied by something, maybe it's divided by something, we can move on from there. We've got the entire expression, and once the trig function's gone, our regular algebra falls out. Just division by 3 brought up these 18s in the denominator there and there. You can do that even when the variable's not necessarily multiplied by something, but maybe if it's divided by something, and division really is just multiplication by a fraction. So if I had root 3 tangent theta over 2 minus 1 is equal to 0, a little algebra gives me that the tangent of theta over 2 was 1 over square root 3, or if I rationalize the denominator, root 3 over 3. Well, hopefully you recognize from the table of values that we did earlier in the semester that this means that theta over 2 has to equal pi over 6. So theta is 2 pi over 6, or pi over 3. Now, what I really should do to keep this on the up and up is note that this is going to be plus k pi because of the periodicity of the tangent function. And down here, I multiplied by 2. So plus 2k pi. Because when I take some value, pi over 3 plus 2k pi, and I plug that in for theta up here, this will get divided by 2, which will turn it into a pi over 6, and this will also get divided by 2, which will turn it into a k pi. So that's the other piece you want to be aware of when you're substituting in for these things. Before you go ahead and isolate the theta, make sure you add on your period, the extra k or 2k pi to deal with the period from there. So that knocks out Chapter 7, and the next video we're going to start talking about Chapter 8, which will introduce some new coordinate systems and give us some interesting functions to look at there.